Okay, I think it's time to start today's session.
Yeah.
So, you see, as those who are present here, I think most of you have had a chance to come to Math Clinic and attend some sessions. And if you, by now you should have understood that Math Clinic is an effort to encourage teaching and learning of mathematics at all levels. So, in an effort to give school teachers an opportunity to prepare and lecture on topics relevant to curriculum, we thought we should start inviting teachers to give presentations prepared by them. So we have the first session today by Mrs. K. Maheshwari. She is from Sir Muthu School in Chennai. So I think with that introduction, let me request her to start her session on pigeonhole principle, which has implications for the curriculum. Maybe it's not directly in the curriculum, but it has implications in the curriculum at school level. So that is the idea. And so, Maheshwari, please.
Thank you, sir. A warm welcome to all of you. Good evening, everyone. As introduced me, I'm Maheshwari. I've been working as a maths faculty for more than 25 years at school level and presently working at Mutha School, Chennai. So I'm happy to be associated with Math Clinic, and I thank Rana sir for giving me this opportunity to take up the session. Thank you, sir, and a warm welcome once again to all of you to this session. So I thought before I start the session, I mean directly onto the topic. We'll just have one small math trick, and we'll look into the idea behind it, or probably how does it work and why. So the trick is this: just have to take any 3-digit number and write it twice. You can use calculators also. And write it twice to make the 6-digit number. And are divided by 7. And then divide the quotient by 11. So whatever is the 6-digit number, your x, y, z, that is the 3-digit number, you're writing it twice in the same order. And you're dividing it by 7. And whatever quotient you get, you're again dividing it by 11. And you're dividing it by 13. You can use the calculator. And what is the result or that we get? We have only 4 participants. Yes, Usha? Anybody else?
We get the same number. We get the same 3-digit number what we have.
Right. Exactly. Can you just take the 3-digit number which you have taken, or can you just tell?
I took it as 1, 2, 3, but it need not be consecutive, is what I feel.
Yeah, it need not. That's fine. So you divide it by 7, 11, and 13. So what is the logic behind this? If anybody can work out. We have only one participant basically, Okay, fine, no problem. So if you look at this, we are dividing it by 7, dividing it by 11, dividing it by 13. So if you look at the logic, we are dividing it actually by the product of these numbers, right? 7, 11, and 13.
Yes.
Right? Yeah. So if you use the calculator, what is the product that you're getting? I think it's
1.
Yeah, just 1001. Is it that? Just check. 7
yeah, 1001.
Right. So any 3-digit number that we get here, let me write it as XYZ only and explain it, because it can be any 3-digit number. So this XYZ can also be written as I can write 1000 XYZ plus XYZ. You can check out with this number. Right?
Yeah.
All right.
Yes.
So this is what we get, and it's divisible by 1001. And you again get, when you divide it by 1001, let me write it here, divided by 1001, you get XYZ. So you take any 3-digit number, and that's how the logic goes, right? Because 7 into 11, 13 is 1001, right? Interesting,
Yes.
right? It's awesome. So maths is really cool and great. So we'll go ahead now with the topic. Let me just remove the highlighter pen. I'll just switch off the pen and then otherwise there'll be ink mark on every slide. Okay. So the topic that we are going to deal with today is the pigeonhole principle. And this pigeonhole principle, I'm just taking the basic part of it for the school level for children 6 to 10. And it states that if there are n items and they're put in m containers, where we're considering the number of items are more and the number of containers are less. So we need, is the screen clear, or is this obstructing the screen?
Yeah, it's clear.
It's clear. It's
okay,
clear.
okay,
You can.
okay, fine.
Are you
So-
recording? You can also.
So then at least one container must contain more than one item, right? So there's a clear example here, like you have got 10 pigeons and you have got only 9 holes or the places where you can fit in these pigeons. So definitely one of it will have one extra, right? So this is the simple, the basic principle, right? It is also called as Dickerlet box principle or the Dickerlet's drawer principle. And this principle actually plays a very important and major role later on in combinatorics or the number theory. Now, this also has been explained in this way in discrete mathematics. The pigeonhole principle states that we have the same logic has been explained in this way, that we put n plus 1 or more pigeon in n pigeonholes, then some pigeonholes will contain 2 or more than 2 pigeons. Now, this can also be actually generalized in this form when you have more than say kn plus 1, where k is a positive integer, and these pigeons are distributed among n holes in such a way that they'll contain k plus 1 pigeons, that at least some of the holes will contain k plus 1 pigeons. So now here also I'll take examples to elaborate on what exactly it means and how to apply it in terms of to take the simple example, when there are there more people who have joined? No, only Usha, you are there. Okay. So we have a bag which contains beads of 2 colors, black and white. So what is the smallest number of beads which can be drawn from the bag without looking? If a person is blindfolded and you just have to pick up the beads. So what is the least number of, the pigeons that, I'm sorry, here the beads, right? Least number of beads that can be taken out from the bag so that they are of same color. So I'll just go ahead with the solution part as we don't have more participants to respond to. So we consider the color of the beads as the pigeonholes, and the beads which are to be drawn would be n plus 1, n is 2. So there'll be 3 beads, applying the pigeonhole principle there. Moving on to the next example. The minimum number of students in a class such that 3 of them are born in the same month. Now here we need to identify what is given and what is what we should consider here as your k and n, and what is it we actually need to find. So here same month and 3 of them. So based on that information, we need to find, minimum number of students in a class such that 3 of them are born in the same month. So now if we look at this, so we are going to use the generalized formula here, right? So based on that, let me just remove this. So what will be the K? Any guesses? I'll just go ahead with the solution because we don't have children here. I thought there'll be more students who will have some response. We'll get more responses. It's okay. Yeah.
Maheshwari,
Yeah.
I will just like to pause you here.
Yeah, please.
Okay, and change your question slightly.
Yeah.
Okay, so
Yeah.
the question to the audience is following. Does everybody remember the day of the week you were born?
Does everybody remember the day of the week?
Day of the week. Say, for example, somebody was born on Monday, somebody. So does everybody remember the day?
No. Yeah. On the day of the, it depends unless the parents insist and keep telling that you were born on this day. Some people may not remember, but yes, most of them will know. Okay. But mother has told that
Even if you don't remember or you don't know, for the time being for today's session,
okay, that everybody remembers. Fine.
Yeah, everybody remembers and give your day something. That you are born on so and so day.
Okay.
Monday, Tuesday, Wednesday, Thursday, somebody. Right? Now my question is or claim is, there are at least 2 persons in our audience who have their birthday on the same day. There is at least 2
people. Right.
Yeah. So can everybody tell what is the day? Probably you can unmute and say, I was born on a Tuesday.
I was born on a Sunday.
Me, Wednesday.
I was born Saturday.
Saturday. Yes.
Friday.
Friday. Yes. Yes.
Thursday.
Thursday. Okay.
Monday.
We already have a repetition.
Yeah, we already have a repetition because
So I was just trying to give everybody a chance to talk.
Very good. That's nice. I was wondering, only we have 4 participants, and I said, okay, there are more. Fine. Okay, good, great. Fine, that's nice.
Okay, so
that's nice. Thank you. Thank you for. I was wondering why we have only 4 participants, and okay, there are 11 participants. Fine.
Okay.
Fine.
We have 11.
Yeah, so that's nice.
By the rule of 100, 10% is good enough.
Correct. And so, so there was can someone just tell that sir was so sure that there will be at least 2 people who will have the same day? So
because our number of participants were more than the number of days in a week.
Right, exactly. So I think we can applaud. That's awesome. Great. So good. So going ahead with the, shall I just go back to that question? Yeah, so we've had 3 of them were born on the same month. And so here we'll consider what will be K that we're going to, this is the hint that we're going to apply this. What will be K in this case and what will be N here? And what is it that we need to find? I'll go back to the questions. Anybody who would like to unmute and see right and wrong, that's immaterial. We just have to think and just say it. So anybody who would like to try it out? 3 of them are born in the same month. So, okay, can anyone figure out the answer? May not be directly applying that. You're able to figure it out in some other way. Probably we can discuss that also.
Maybe we can ask, suppose the number of students is say 30.
Mm-hmm.
Okay.
Okay.
is it like, will this number work?
Yeah. Yeah. If the number of students is 30, then will this situation
Can you
we get,
ensure that
3 of them will be born on the same month?
right?
Yeah. So can this condition be satisfied?
Let us see two numbers, 20 and 30.
Yeah, 20, 25, any such numbers, you can try it out. And yeah, anybody who would
Basically,
like to,
there are 12 months in a year. And,
exactly.
yeah, so you need minimum 36 plus 1, 37. Or
Okay.
30. Yeah,
We're talking about minimum number
yeah,
of
minimum number.
students. Minimum, so that we have at least, 3 people born in the same month. This pigeonhole principle, basically, it's only for minimum, least, at least, that is the situation, right? So what you said is correct, that it's 3 people can, it's a 36, but we are looking at 30, even if we have 36 or 37, we'll have 3 people, but we are looking at the minimum number of students. This is not the minimum. Even if we have 40, we'll have 3 people born in the same month, right? We're looking at the minimum number. So what could be the minimum number? So if 2 people are born in the same month, 24 for sure, we can make it like that. Then now you can figure out. 36 is definitely not the minimum, or it is the minimum.
No, then we will have 25, right? 2 plus 1.
Anybody else would like to say anything? Any other opinion, or would like to contradict anything? He says 25. So are we all clear with this 25, or do we think 36 should be the 36 or 37? We're just thinking there's nothing wrong in coming up with solutions and our own reasoning part, right? So now let's apply the principle. Let me just remove this pen. Now let's apply the pigeonhole principle and see how easy it becomes. Once you identify what is K and what is N, that confusion part gets eliminated actually. That whether it's 36 or whether it's 20 or whether it's the number of months are 12. And according to the given condition that you're applying, I'll just go to the previous slide. See, this is the generalized formula. Kn plus 1 are the pigeons which are distributed among n holes. So K plus 1 are the least number of pigeons. We need to figure out this, right? So what is K here? Just go on. Yeah, is what we are figuring it out, right? So N is the number of months, and we need to have at least 3 students in the same month. So your K plus 1 is 3, so K is 2, right? Now the minimum number of students is obtained by this formula Kn plus 1, right? It's 25. So what you said, 25 is the right answer. I'll just go to the question, back to the question where we were discussing this. Do you all agree to it now? Is there any other clarification that is needed?
No, it's clear.
It's quite clear. Great. Thank you. So we can go ahead. Fine. So moving on to the next question. I think this, all of you will be quickly able to get it now. Yeah. There's a box which contains different color balls, and they are in different numbers, like blue is 10 and red is 20, green is 8, yellow is 15, white 25, and so on. How many balls must be chosen to ensure? Now again, we are talking about the minimum number of balls that to be chosen. Okay. so that we ensure that, I'm sorry, I'm selecting the pen and it, yeah. To ensure that we have 12 balls of the same color. 12 balls of the same color. This is the given information. And 12 balls of the same color. So can we apply the same logic here as applied in the previous question? What could be K here and what could be the N? So what would be K?
Blue and green cannot be taken into account, right?
Okay. Blue and green cannot be taken into account. Why? Like 12 balls. Okay.
Yeah, less than 12.
Right, less than 12 minimum. Okay. Okay. So let me erase this because it's not necessary that you have to figure out this. Yes, as you are saying, okay, let's go ahead by the reasoning first, and then we'll go ahead with the pigeonhole principle. That's fine. Yeah. Because the moment I write this, it'll be like we'll be restricting the thinking in one direction. So there can be various ways of working it out. Right. Yes. Any other opinions, suggestions? How will you ensure that we have 12 balls of the same color? So that we choose, I mean, we have to choose the minimum number of balls. How many balls will you choose from out of all these given balls so that we have 12 balls of the same color? Of course, we are, it's like blindfolded and we are selecting the balls from the bag, which contains these different colored balls. The blue, red, green, yellow, white of different numbers, 10, 28, 15, 25. We need to have 12 of the same color. Any
K plus
students?
1.
Yeah.
K plus 1
Okay.
is 12.
Yeah. Do we have any students also here? Anyone who has, or all teachers and any students here have joined it?
I think for the time being, all are students.
Okay, fine. No, I just basically wanted those who are studying, like, okay, fine. So all of us are students, right? Great. That's nice. Actually, we all are students. Lifelong, we are students. We keep learning, so, throughout our life. Yeah, please go ahead. Yeah, please go ahead. By reasoning also, we can work it out. We need 12 balls. So what is the minimum number of balls? Like we are blindfolded and you have to pick up the balls from the bag. So how many will you? It's just like a game. You need to win the game, and if you can win the game only if you get 12 balls of the same color. You're blindfolded. So
Yeah, but
how many balls will you pick up?
Are you allowed to see the balls to start with?
No, that's what you're blindfolded.
To start with.
To start with also no. It doesn't matter. Does it matter? You will know that there are 10 blue balls, 20.
Right.
That you will know. That information is known. Like you know that in this bag, this many blue balls, this many red balls, this many green balls, and this many yellow and white balls are there. That information is given. But they are in a bag, and you go to a fair, you are playing this game, you have to win the game. So we are also excited. We need to win, right? It's a lucky draw or whatever. So how many balls will you pick up? If you get 12 of the same color, anybody, any guesses? It's see, we're not looking at right or wrong. Any guesses? Anything is fine. But how do you make that guess, or what is the reason behind? That's it. That's what we need to discuss.
Yeah, I think you're missing the at least part.
Yeah.
You have to reiterate.
Yeah. How many
much,
balls must be chosen to ensure that they
no,
have at least, yeah,
that at least
12
word
balls
is
of-
missing. So
right,
that is
minimum.
important.
Yeah, minimum or at least, yeah, that should be there.
That should be there.
Minimum
Otherwise,
or at least. Correct. Yeah, I missed out on that, but I read it out. So, okay, fine.
you can write with your pen.
Yeah, I'll write.
Minimum balls.
Yeah.
Hello, madam.
Yes.
So it may happen that in first 10 draws,
Yeah.
we will remove 10 blue balls. Then in next 8 draws, we may remove 8 green balls.
Okay.
Then in next 11, we may get 11 red.
Okay.
Then 11 yellow, and maybe then 11 white. So
Right.
11 into 333 plus 18.
Mhm.
And the next one, we are sure that, no, you are saying minimum, no?
Yeah.
Minimum. Your good name, please, because I didn't get who.
Rajesh.
I'm Rajesh.
Rajesh. Yes, Rajesh. See, the idea is just think of that. We go and play those games, right? In the fair, when you just have to close your eyes and pick up, right? So here you get only one chance to pick up as many balls as you want, so that you get 12 balls. But the condition is that should be the minimum number of balls that you pick up.
Hello, ma'am.
Mhm.
Is it the answer is 52?
Okay, can you just elaborate on it?
Yeah. So suppose if we pick up 11 yellow balls, 11 white balls, 11 red balls, this gives 33. And then we pick 8 green balls and 10 blue balls.
Okay.
So this gives 43 and 51. And then we pick one more ball. So that would be from either red, yellow, or white. So this would be, I mean, at least 12 balls would be there of the same color.
Same color. Okay. So you say 50?
52.
52. Okay.
But
yeah.
I just want to say that here you are able to see that picking up blue or red or something. But our condition is that you are not allowed to see the balls you are picking. Is it, Rachna? Is it clear?
Yes, sir.
See, you are told this data is given to you. Then your eyes are closed. आंखों में पट्टी बांध देते हैं. Okay.
Yes, sir.
You are allowed to pick up balls. पहली ball निकाली, दूसरी निकाली. So what is the minimum number?
In one go. In one go, how many balls will you pick up so that you get 12 balls in your hand of the same color? You got it? In one go, say you pick up 10 balls. Those 10 may be of 5 different colors, 2 balls of each, right? I pick up, say, 20. So 20 can be of one same color also, or 20 can be of 5 different colors also, 4 each, right? To be sure, we have to be sure of that we get 12 balls of the same color. So how many balls should I pick up in one go from that bag?
So shall I put your question in another way?
Yeah, please. Yeah.
The lady luck will not help you unless you have that many balls picked at one go. That is the thing. अगर उससे कम निकाली तो आप श्योरली नहीं जीतोगे. ये भी श्योर नहीं है कि उस नंबर पे आप जीत जाओगे, बट एटलीस्ट उतना नंबर होना चाहिए बॉल्स का जो आप पिकअप करो. चांस है कि आप जीत सकते हो. Then there is a chance. So what is that number which gives you a chance to win? The minimum number जो आपको चांस देता है जीतने का.
अभी जितने total balls हैं उसमें से do we have from the north also the participants?
I don't know. I'm just trying to say in
okay.
Hindi. Somebody will understand Hindi. Somebody...
Okay. Can you raise your hand if there are people from the north who understand Hindi? Because I don't have a problem. I can also repeat it in case. Are they?
The video is switched off. We are not able to.
Oh.
Okay. Video is
not Maheshwari. We are able to see. Not.
No, I think the slides are visible.
Yes. Even if we raise a hand, I don't think.
Okay. Okay. Okay, fine. So, okay, so I'll just go ahead. So if there is somebody who is having a language problem, I can just repeat it also. यहाँ पे हमारे पास इतने बॉल निकालने हैं, कम से कम बॉल पूरे बैग में जितने बॉल्स उसमें से कम इतने बॉल निकालो कि हमारे पास 12 बॉल एक कलर के हों. So, right. So this is the whole idea. So let's check if 52 what she said, and anybody else has any other opinion can also. Yeah. Going further with the solution part. Now the categories, you know, those different color balls which we had. How many? 5 different colors. And why are we taking k plus 1 as 12? Because that's the minimum number of balls you should have of the same color. Right, minimum number which you should have of the same color. So k is 11. Now substituting m is equal to kn plus 1. So that makes your whole work easy. And whatever was the logical thinking, great. We were doing, understanding it. Can someone also elaborate logically? How do we get that figure? If we got 56, right? So anything that you can figure out here that, okay, this could be, if I would have taken 30, that could be red and blue or red and white. It could be 2 colors maximum, right? If I would have taken, say, 45 or 50, 55, it would have been, see, what could it be? 20. Once again, let me just pause that. So something that helps you to understand here also, that 20, 25, and 15. So what would be the next, you know, it's something like that. Anybody who can help out or explain it? Or shall I just go ahead? Okay. Okay, with this pigeonhole principle, application part is clear. The generalized formula. There are 5 categories. And
no, I have one question.
Yeah, please.
So why 52 will not work? Can you just explain that?
Yeah.
Why 52 will not work?
Yeah, why 52 won't work, right? Let me just take this one. Let's check this, 25 and 20. Yeah, 52 should work as you say, right?
The total number of balls which are eligible are 60.
So
20 plus 15
let's take. So this is 20. Yeah. Yeah, please go ahead. Yeah.
The total number of balls which will satisfy the condition is red, yellow, and white alone.
Okay.
So 20 plus 15 plus 25 is altogether 60 balls.
Why are we taking this? And why are we not taking 10, 8, or 15?
Because they don't satisfy the 12 balls of the same color, which is not possible.
Right. So we will not take the blue and the green. Fine. And we need to find the minimum number. So we are right. So 25, 20, and 15. Right. Now here, as one of our participant has asked, why not 52? 52 can also give us 12 balls of the same color. Why not 52?
12 balls.
If we take 52 balls, then why not 12 of the same color? Now there are 5, right? There are 5 different colors, right? So let me take 5 boxes. There are 5 different colors, right? And we're taking 52, right? So I can have here 1 8 and the other all 10. Now just think, we can also have, now how much we have? 48, and there's a difference of 3. So we can have here some 13. Let me take this as blue, and I'll keep this as green, say red, yellow, what is the other one? White, right? So I can increase this to 13. Still it gives me 50 or 14, right? So is it giving me 3 colors of the, yes, it is giving me 12 balls of the same color. Yeah. So we can make this as 11, right? 11 and 11, but that is not assured.
No, the first one cannot be 11. Blue is only 10.
Okay, so leave off that.
Yeah,
We can
basically,
make,
I feel like because we have to discount the fact that there are some balls which do not satisfy the 12 color
Correct.
criteria. So
Correct.
we have to discount from 56 that one. So ultimate answer will be 52. 11 minus 10 will be, we are left with how many? Basically 1 minus the blue balls has to be discounted, green balls has to be discounted. So totally 56 minus 3 minus 1. So yeah, because ultimately anything 11 plus 1 is 12. So we have to start from the fact that we need a minimum 11 balls. Now blue balls are no.
Okay, fine.
To
fine,
make the
fine.
number minimum of 12,
correct.
you need 11 plus 1, right? But because we have blue only 10, so we have to discount the 10. So
Okay.
11 minus 10 is 1 that we have to discount. And then green is 8, so we have to discount another 3. So by the pigeonhole principle, you get a minimum 56, whereas 2 balls do not satisfy this criteria. Hence, you will discount additionally minus 1 and minus 3. So total will be 52.
Okay.
Want to
So
repeat
what if
everybody?
yeah.
Hello.
Yeah, so if 52 balls are taken out in one go, you mean we will get 12 balls of the same color?
Yes.
But what if you get these blue and green balls along with it when you're taking it? Because they're all in the same bag. You still get 12 balls of the same color?
Yeah, the maximum blue can reach is 10 and green can reach is 8. And if you put the other 3, 11, 11, 11, then what is it? It's 33 plus 18.
18.
Yeah, it's 51. So anything beyond that, that one more cannot be blue and green.
It from red or yellow.
It has to be one of these. Yeah. Right. So anybody else who would like to add on to this anything? It was a nice discussion.
But does it mean, yes, but does it mean that pigeonhole principle isn't applicable here? Sir?
Rana sir, would you like to add on to this anything, or anybody else who would like to add on to it? That we're getting 52 and using the pigeonhole principle, we get 56. So how do we justify this? Yeah.
If instead of this bounds on each numbers, if you know that there are unlimited number of balls in each 5 categories or in each 5 colors.
Okay.
Okay. Then the answer would be 56. But now there is a bound. You are asking for 12 same color balls. but then two of them are less than 12.
Right.
So that's why this -4, you have to do it.
Okay. Okay. So if all numbers were should have been greater than 12,
Yes.
is a necessary condition.
Yeah.
Okay.
In that case, the answer would be 56.
See, this is one of the examples. You say blindly don't apply algorithms.
Yeah.
In a class. Okay.
Right.
If you blindly apply the algorithm of pigeonhole principle, then you will get some.
Then it will not work, right?
Which is not a very correct answer from that point of view.
Correct. So we cannot apply it here.
Example from that point of view.
Right. So keeping that in mind, as you also said, and yes. So if we apply that directly, what will happen here? We'll lead to a solution which is 56 and which will not apply in this particular condition, right? And because we have the number of, as rightly said by Soumya, yeah. Perfect. Thank you so much. Now, moving further with the next question, find the minimum number of students in a class to be sure that 6 of them are born in the same month. Minimum number of students in a class to be sure that 6 of them are born in the same month.
Are you saying something about the number of students or not?
You have to find the minimum number of students.
No. How many students are there? For example,
that is what we have to calculate. Minimum number of students
total
in a
number
class.
of students.
Yeah,
Total
it should be there in the class. So here now the previous question was we were calculating this was given like the number of students or the number of balls or the number of marbles that was given. Here it is, now we are calculating the minimum number of students that should be there so that we are sure that 6 of them are born in the same month. It's something like in a hall, how many people should be there so that 6 of them we know are sure to be born in the same month.
Yeah.
61.
One answer is already there. Yeah.
Yeah. Can you just explain it, Anna? How do we get that answer?
So we have 12 months.
Okay.
So suppose we have in January 5 people.
Okay.
February 5 people. Like that.
Okay.
All the 12 months we have 5 people.
Okay.
So altogether it will be 60
right.
people. If we have one more people extra, there should be 6 number of people.
Okay.
With the same month.
Fine. So 61. Anybody would like to add on to it or any other way of that you can arrive at or anything? Do you get a minimum number less than this? Or do you all agree that 61 is minimum? And after that, can we apply a pigeonhole principle here? Can we work out with the pigeonhole, the generalized formula?
K plus 1 is equal to 6.
Okay. So the minimum number M.
Should we take it in terms of
so N would be the number of months. Yeah, please go ahead. Anybody else?
Yeah, I think the answer is.
So we get K as 5.
Yeah.
And then we substitute and we get. So we can apply the principle here, right? I'll go ahead with the next example. So now we have 21 boys having a total of 200 rupees in notes. Here you need to prove that it is possible to find two boys who have the same amount of money. You have to prove that it is possible to find two boys who have the same amount of money. Same amount of money. There are 21 boys, have a total of 200 rupees. So how do we go about the proof part? Can we apply the directly any pigeonhole principle here? You need to do the, it's given that there will be at least two boys having the same amount. We just have to prove it.
So here notes means what? Like
it's
same denomination or not?
No, it's not with same denomination. It's just currency. They have 200 rupees.
Oh,
it's not one. It's not just one 200 rupees. It's like in different denominations or whatever. So 21 boys are having a total. They pulled up the money. It's like it has nothing to do with the
which notes are allowed, like
that's what
denominations doesn't come here, right?
There's no denomination. There could be it's not denomination, nothing to do with the denomination. It could be coins, notes, or it's just the currency. That's it. The mentioning the currency, that rupees and notes. So just rupees. Even if we remove this, also should be fine. 200 rupees.
200 balls, you can say.
Okay. Yeah.
To make it.
It will be
same amount, same number of balls. 200 balls.
It has nothing to do with the denomination, right?
No, but you are not allowing 50 paisa, right?
There are Soumya, let us reframe the question.
It could be in terms of, let's take it as not a fraction, but it will be integers, like,
Right. So minimum one in multiples of 1 rupee.
It should be, that's why it said in notes. So now, it's not something to do with currency, the denomination, but yes, we cannot allow 5 paisa or 10 paisa, or that is a part of one. You cannot take a part of one. Like when we, it's one whole that you have to take in terms of multiples of one.
We may say now.
Just let me reframe. 51 boys have a total of 200 marbles.
Okay, fine.
Prove that it is possible to find two boys who have the same number of marbles.
Perfect.
Is it clear now?
Yeah.
Total number of
yes, sir.
200 marbles.
Same amount of marbles. Okay.
Same number of marbles. Marbles. That's all.
Yeah, fine. Same number of marbles.
So this also illustrates something. Framing a question
right,
is also important. Like there shouldn't be any misunderstanding.
Perfect.
Of what kind of data is given.
Correct.
So that is for that. If you some of us are teachers, very important thing to make it less cumbersome to understand the question itself.
Most of the time it does happen that we frame a question keeping something in mind, and when the children see it, they see it in different ways, like in notes, yes, in currencies or its denominations. Is it part of it, like 50 paisa, 5 paisa, 10 paisa, even that is taken into consideration or not? So there are, that's a good point. Actually, when we teachers also put forth a question, we need to, in front of the children, we need to look into all this aspect.
I think you can leave this question as a homework.
Okay.
Ma'am,
Yeah.
So is it so that every boy has some amount of money, or it may happen that some of the boys do not have any amount of money?
Maybe. Okay.
So what is the condition I'm asking?
There's no condition. There's no condition. It just says prove that it is possible to find that two boys have the same number of marbles. The total number of marbles is 200. These 21 boys are having total number of marbles as 200. These are the boys, and this is the total number of marbles. They've added.
Can we assume the other way, where what if they don't? What if if they are going to have the same number? I should number them as 1, 2, 3 like that.
Yeah, we can. As the number, yeah. If one person has one marble, two marbles, we can try it out that way also. Yes.
I should arrive at some contradiction here, because it's a proof that, and if I assume that all 21 are having distinct ones, then it should be 20.
So even if one person has 0, this is what is your right?
1
so
plus
you will get
a sum of
ma'am.
Yes, pardon. Yes.
Shall I say something?
Yeah, please.
Yeah. So suppose if we assume that all the boys, so we take two conditions. So in the first case, we consider that all the boys have some amount of money, right?
Right.
So we add 1 plus 2 plus 3 up till 21. Okay.
Okay.
So that gives 231. Right. So which is more than 200. Okay. Now, if I subtract 11 from it, so suppose the 11th number of boy does not have any money. No. Yeah. Suppose 11th number of boy does not have any money. So that would give me what? 200. No, 210. And suppose the 10th number of boy also does not have any money. So that would give me 200.
Correct.
So this gives a contradiction.
Right.
I mean, so that means the case we started with no.
When you say that 10 people do not have money, it already has satisfied that there are at least 2 people who are having 0 money or 0 balls.
Correct. So the condition is it's proved. So yes, we will we can arrive at the result by contradiction. Fine. One more thing I wanted to I mean, just take that into consideration. Like when you're adding the numbers, we can even introduce this in class 6, 7 also. We need not to wait for this number theory to be introduced in 10, 11. That simple addition, 1 plus 2 plus 3 till 20, how to add it.
And
So that is one idea was there in my mind why I took this question, just to tell that this summation can be introduced in lower classes also. We need not to wait for them to reach 10th or 11th and then introduce this with the
Maheshwari, your audio is good.
Audio is breaking.
Yeah.
So this was now, is it fine? So yeah. Fine. So this was the idea behind why I took this. So it was rupees or notes or marbles that I wanted to bring into this particular summation formula, which can be introduced in lower classes also. So that was the idea. And great that you all have come up with the solution. That's fine. I'll wind up. I think it's going to be, yeah. So I will just quickly go ahead.
But how is it an application of pigeonhole principle?
Yeah.
Madam, I want to say something.
Yeah, please.
We are having 21 people. So there are 21 C2 ways to select 2. And I think 21 C2 is 21 into 10, that is 210. And we want to fit them now into 1 to 200. Okay, these pairs. So some pair will have that is, they will go in the same box. This way we may able to apply.
Right. And now this is what is your pigeonhole principle, the combinatorics which you are applying, the number theory. this is where your pigeonhole principle comes in. Further application of it. Yeah.
I think it's time to probably
wind up. I'll just quickly now just wind up. Yeah. So I think I'll so by contradiction we have arrived at it. So okay. I'll just skip all these, the birthday problems and the other problems, where probability also have combined there. So it's a simple math concept. This does not, I mean, there are a lot of interesting facts which we can take it as small questions and puzzles in classes without telling them that it's a pigeonhole principle. We can, you know, make our children solve these questions even at lower levels. So we don't have to explain what is a pigeonhole principle, but we can just give them as small puzzles. So where they'll come out with, you know, how without even knowing what it is and how it is, without even applying the logic, they can. This was just a practical application of it. So I just hit all this. Go ahead. So I basically took this. I did not go into further the application part of it, so that it can be applied at lower classes, even 6th, 7th, 8th, without telling them what is the pigeonhole principle. We can introduce these simple questions in form of puzzles. That was the whole idea. So it helps in decision making. So they develop these strategies, the various strategies of logical reasoning, and that's it. So I'll wind up with this, and
I just want to have a one small discussion.
Yeah.
I want to ask somebody who has not spoken probably in the whole thing. I think Trinath, have you? Hello, are you there, Trinath? Hello. Trinath, you can unmute and say something if you're there. Okay. What about Rahul? Rahul, are you there?
Yes, I'm here.
Okay, Rahul, let me ask you a question. You go to a bank.
Okay.
Okay. And you want to withdraw 10,000 rupees.
Okay.
And the cashier says he has only 100 rupee notes.
Okay.
So he gives you a bundle of 100 rupee notes and says, this is 10,000.
Yes.
Right? So how many notes should be there?
100.
100.
Yeah.
Cashier says there are 100 and he says to you, you count.
Right.
And you count, you think they are 99.
Yeah.
What will you do?
I will question the cashier.
So you will give it back to the cashier and say, they are 99, right?
Yeah.
Now cashier counts again. Okay, he puts it in the machine. Now notice the machines for counting, right?
Yeah.
And machine counts it 100.
Yeah.
And gives you, no, he says they are 100. You again count and you say, no, they are 99.
Yes.
So what is the true answer? Whether how many notes the bundle has, 100 or 90, 99?
99.
Why? Because you say so?
Why should I believe the machine? I believe myself.
You believe myself, not the machine. Okay.
Yeah.
And you give it to a friend who is also gone with you to the bank and say you ask him to count. He also says that he says actually there are 101.
Okay.
now you are in a dilemma.
Okay. Very interesting.
So there are three answers possible. One is 101 given by your friend. You can all switch on your video if you think it is okay. You can switch on your video. So your friend says 101 notes are there. You say there are 100. And the cashier says, cashier says 100, you say 99.
Yeah.
So which is the right answer?
It's still 99.
It's still 99?
Yeah.
You want to believe yourself?
Yes.
Even if your counting is wrong?
Yeah.
It's possible, right?
Yeah.
But that bundle is a physical quantity which has a fixed number, a unique number of notes. Whether the bank counts it, whether you count it or your friend counts it, it is the same number.
Yes.
Right? A unique number. And,
yes.
And that number is assured by pigeonhole principle. So let me make it a more mathematical one if you want it. How many stars are there?
Okay.
How many stars are there which you can sort of, okay, stars will be too much probably because somebody say, I can't see that one, either blinking and something like that. You got a big set, big collection, a big set.
Okay.
Lot of elements are there. How do I ensure it has a unique number of elements in it? You understand the problem now, Rahul?
No, sir. One second. Can you come on?
Okay. Let us say you have got a sack full of wheat grains.
Okay.
Right?
Yeah.
The number of grains in that wheat sack, गेहूं की बोरी के अंदर कितने wheat grains हैं, वो तो एक ही नंबर आंसर आ सकता है ना?
Yeah.
Whether you count or I count it or somebody else counts it.
Right.
So how do I ensure the number of grains in that sack of wheat unique? एक ने एक ही नंबर है, चाहे बहुत बड़ा नंबर है, कोई प्रॉब्लम नहीं है, मगर एक ही है. How do I ensure that? कोई चीज ऐसी है जो मेरे को अश्योर करे, हाँ एक ही ये नंबर है.
That's how our security system, the lock system, all those keys, the unique number works on, right?
I'm not going into that.
Yeah, okay, fine. Yeah.
You understand? So imagine that
Yes.
Okay, is a set in which the number of elements are the grains.
Right.
Number of elements in a set, either they are infinite or they are finite, and that finite number is unique.
Right.
How that uniqueness is determined? It is determined by pigeonhole principle. So pigeonhole principle has application in defining what is the cardinality of a finite set. The pigeonhole principle can also be stated that there is only one. If you have a 1-1 onto map bijection,
Bijection.
1, 2, 3 up to n, and 1, 2, 3 up to m. Then m has equal to n. This is possible if and only if m is equal. That is pigeonhole principle, and that ensures. Okay.
Right.
If you are teaching 10th, 11th, or 9th set theory and finite set number of elements, how is the uniqueness coming? That is coming from pigeonhole principle. I think let me here and ask anybody else wants to say something.
Yeah, so I'm still wondering one question now. Like, whether does there exist a person in the world who has the exactly same number of hairs as of me in my head?
Okay. I will not be one of them because I have very less number. It's a good question. Pose it in the class. Okay.
Yeah, sure, sir.
Okay. Yeah. Please fill up the feedback form before you leave. If anybody else has a question, remark, or say something, so please. As Maheshwari said, it's a very simple principle which we can excite students about very simple problems in the classroom and show applications of mathematics at various levels. So thank you, Maheshwari, for coming over.
Thank you, sir. Thank you for giving me this opportunity. It was nice experience.
And please spread the word if any other teacher would like to give a presentation on a topic relevant at school level. Please send me an email. My email is ikrana@gmail.com.
Yes, sir.
So with that, let me wind up the session if no more questions are there. Sessions. Okay, take care and thank you everybody for coming.
Thank you, sir.
Thank you, sir. Thank you all.
Thank you, sir.
Thank you, Maheshwari. Excellent.
Thank you, everybody. Thank you so much. Thank you, Usha. You were also there when I was preparing. Usha was there, which was helping. She was like, giving me ideas. Okay, just do it. This, that. So Usha was also there. So next time Usha can actually give a session.
Anna, sir, it's really a very, very nice platform for us to really.
Please.
Brainstorm. Basically, to brainstorm. For
example, you can pick up some topic and some mistakes students make and bring over those questions and ask what are the mistakes this person is making.
Right.
These are the so math clinic, your and patients are there to need help. So do come over. Thank you very much.